All right, welcome. We'll start in just a minute or two. So again, if you do have questions, feel free to type them in the chat, and we're going to be picking up chapter 4 here. It's where we left off. Just a second. Okay, so we're going to pick up with lecturing on chapter 4. Just a couple of reminders. Again, if you do have questions, feel free to type in the chat. Also, I did grade your first exams. And again, a reminder on the exams that I did go over every question, both on the one that the computer graded and then also your work as well. And I made appropriate adjustments based on your work and then also the computer and stuff like that. Remember that when you do show work, you do need to show all the work for those problems. That includes the setup, the dimensional analysis, like I said, to do with the units, the significant figures, and all those type of stuff. So again, if there could have been a situation where maybe you got the correct answer, but you did not show all the work. So obviously your points total was adjusted accordingly. So in future, make sure again you remember that if there's any problems that have work associated with it, you're expected to show up the setup, the units, everything like we've done in class before. Okay, so you should also be able to see the markings that I did on the paper that you uploaded. But again, I don't think I'm sure you'll be able to. You should be able to see the actual exam too, but it won't show any corrections or anything like that. All right. All right. So we're going to pick up here then in chapter 4, and we were talking about bonding, and we were talking about types of bonds, and I think we finished up here talking about the different types of bonds. And we could use a chart such as what we have here on the screen. Again, this is the electronegativity chart. And if you do need that chart, obviously it will be provided for you. This is the chart where we could use to determine whether or not a bond is polar. So a reminder that what we use this for is really what is sometimes referred to as bond polarity. And bond polarity is pretty much what it sounds like. It really is just between, say, two atoms, whether or not that bond is polar, that bond is non-polar, or even that bond is ionic. Remember, the differences between those types of bonding is an ionic bond. There is no sharing of electrons, so there's a transfer of electrons from the metal to the non-metal. Again, what holds that together is the positive and negative attraction between the two ions. And that's different than a covalent bond, which can be polar or non-polar. And again, if it's polar, what that means is the electrons are being shared. but they are being shared unequally. And if it is nonpolar, that means that the electrons are still being shared, but they're being shared equally. So we can use electronegativity values and sort of a general sort of breakup in terms of differences in electronegativity values. So if we have a difference in electronegativity, which is what the delta En means, if the difference is between 0 to 0.4, it's considered a nonpolar. If I don't click, considered a nonpolar covalent bond. Again, that's covalent. So here, even we would expect the electrons to be shared equally between those. If it's above 0.4, so like 0.5 to below 2, it's considered a polar bond, which again is covalent. So we're going to be sharing those electrons. So unequally sharing here with our polar, equal sharing with our nonpolar. And then typically if it's above 2, you typically have some type of ionic bond, which is no sharing, electron transfer. So electron transfer, no sharing. And it's a pretty simple sort of table to use. Remember, 4 is the most electronegative, 0 not so much. So fluorine is the most electronegative atom you could have. So for example, if you had a bond between, say, carbon and oxygen, you could go to this table, look up the values. You see carbon is 2.5. You see oxygen is 3.5. So you can take the difference in electronegativity, and you can take 3.5 minus 2.5 gives you a difference of 1. And again, that difference of 1 would put you right here in this range. And we would think that the bond here is polar between carbon and hydrogen. That means that the electrons will not be shared equally, and it always will point towards the side that is more electronegative. So we sometimes could represent that with these dipole arrows, where it points to the side that's more negative and the side that is kind of more positive. So it always points to these arrows here to the more electronegative side. And again, that's what these arrows are. You'll sometimes see these arrows that have this little kind of tail on the end of it. And again, that's sometimes what is referred to as a bond dipole arrow. And again, it's used to show the difference in electronegativity between two atoms within a bond. Now, we also talked about, again, if you take something like, say, potassium fluoride, potassium fluoride is 0.8 potassium, and the fluorine is 4. So again, if you take the difference in electronegativity, you have 4 minus 0.8 equals 3.2. That obviously is above 2, and that would give you an ionic bond. Really, for an ionic bond, you actually don't even need this table, because you should know that it is a metal and a non-metal together. So pretty much if you have that combination, this table is really not even needed. You'll be able to determine it's an ionic bond in that case. We also saw that you can, in addition, obviously, if you have two elements that are the same, so if you had F2 like we saw the other day, that would be 4 and 4, which obviously gives you a difference of 0 when you subtract 4 minus 4. And that obviously is a nonpolar bond. And again, sometimes people will call this type of bond where you have a 0 in electronegativity also a pure covalent bond, again, because it's perfect equal sharing. So there's also a relationship known sometimes as the diagonal relationship, like we see here with nitrogen and we see here with chlorine. Although nitrogen is further up, chlorine is further to the right, so they sort of cancel each other out. So technically speaking, if you had a bond between nitrogen and chlorine, they actually both would have the exact same value, and the difference in electronegativity here would be 0, and this would be a nonpolar bond. So there is a lot of that sort of diagonal relationship that you see on the periodic table in terms of electronegativity. One thing that you do know for sure, though, is if something is in the same period heading in this direction For example, if you compared the carbon and the oxygen like we did previously, because they are in the same period on the periodic table, oxygen is further to the right. You actually don't need the table either, because it's safe to assume that oxygen would be more electronegative in that case. And same thing if you were doing something in the same group, like this guy right here. We have our oxygen and our sulfur. Again, our oxygen and our sulfur would be in the same group, with the oxygen being higher up, and we would expect the oxygen to be more electronegative in that case. So there's a lot of cases where you can just use the general trend on the periodic table for electronegativity, which again is electronegativity increases as you go to the right and decreases as you come down. And a lot of times you can, without having these actual numbers here, you could actually just use sort of the general trend to sort of figure things out. Any questions on electronegativity? And again, if you do need the numbers, they will be provided for you. If they are not provided for you, that pretty much means you probably could use the general trend on the periodic table to determine that. So just a reminder that it is it is the electronegativity that really helps us decide not if the entire molecule, for example, which we'll talk about later, is polar or non-polar, but really between two individual elements within a bond, or the difference between those two guys basically going to give you a polar bond, a non-polar bond, or again, an ionic bond. Usually in most cases we use electronegativity for covalent bonding. So as we talked about last time as well, I think, again, if we get something that is very widely different in terms of electronegativity, we would expect, for example, electrons not to be shared equally. And in some cases it may be transferred, while we would expect when we have guys that are near each other on the periodic table that they would be more apt to share electrons. And that is why when we look at something like this, if you remember from naming and everything, it is our nonmetals that basically will share electrons. And if you think about the periodic table, all the nonmetals are essentially right here in the same location, which means they all have similar sort of electronegativity values. So when two nonmetals get together, the best that they're going to be able to do is they're going to decide to share those electrons rather than transferring electrons. And that's different when we get a nonmetal, which again is up here, and our metals, which are on this side of the periodic table. When those two guys come together, we have a big difference in electronegativity values. And that's why in those cases, when we take a metal and a non-metal together, which makes an ionic bond, we expect those electrons to be transferred because of that great difference in electronegativity values. And here's just a table. I think you have a similar one in your book. Again, is sort of where we cut it off. Again, less than 0.5, so usually about 0.4 in terms of the cutoff for electronegativity is sort of the big cutoff for a nonpolar bond. And really that cutoff is really for the carbon-hydrogen bond, which I believe is 2.1, more like 2.1 and 2.5. And that difference in electronegativity gives you that difference of 0.4. The carbon-hydrogen bond is considered nonpolar. And that's a big bond that we see in something like organic chemistry, for example. Most organic molecules are carbons and hydrogens bound together, and they are nonpolar. And so that's why that 0.4 cutoff is there. As we also talked about, if the difference in electronegativity is not exactly 0, but it is, say, 0.4 or less, if it is 0.4 or less, even though it's still considered equal sharing of electrons, there is still an element of unequal sharing happening, but very, very small. But there's still that aspect of it not being shared perfectly equal with each other. All right. So the next thing we're going to talk about are the steps to follow when you write or draw Lewis structures. And basically, we talked about drawing Lewis structures for our ionic compounds. Here we're going to draw Lewis structures for our covalent compounds. And you definitely want to sort of follow these steps in order. If you follow these steps in order, you will pretty much end up with the correct picture or a pretty good Lewis structure picture. If you decide not to follow these in order and you decide to do sort of what I refer to sometimes as sort of piecework, and what I mean by that is everybody draws the individual Lewis dot symbols. They try to figure out, where all the electrons go and everything like that. Most of the time, people will end up with the wrong picture, too many electrons, not enough electrons, wrong number of bonds. So it's important to sort of follow these steps. They should lead you to a pretty good Lewis structure when it's all said and done, especially for our class. So the first thing you want to do is think about when you're given a formula and you want to write or draw the Lewis structure. Again, Lewis structure, going to use those Lewis dot symbols like we did in the previous chapter. Remember that those Lewis dot symbols basically is the symbol, a dot to represent each valence electron. And again, one of the main rules is essentially no more than our 2 dots per side. That gives us sort of a magic number in terms of bonding, which is 8. And it maxes out at the same number of electrons as the noble gases, which again is really the whole purpose of all types of bonding, ionic bonding, covalent bonding, which we're talking about here. The purpose is for everybody to get to that noble gas configuration, which is group 8 on the periodic table, and be very, very stable. Now, the first thing you want to do is, just to make sure, I think we did talk about the octet rule, which is 8 valence electrons around it. Remember, everybody wants to get to that 8. The exception is hydrogen. So the goal is to get to that octet rule, which is 8 valence electrons. Again, except for hydrogen, which should only have 2 valence electrons. So no more than 2. Again, as we talked about, hydrogen just needs to get to helium on the periodic table to be stable, which is just 1 more electron. So when you go to draw these Lewis structures, the first thing you want to do is draw the skeletal structure for the compound. So basically this is, in most cases, you'll be given a formula. You want to think about the logical way to arrange it. So a couple things that could help you in that is, in general, in the center of the molecule is the least electronegative atom. So in the center should always go to the least electronegative atom. We will never find hydrogen or fluorine in the middle or the center positions in the Lewis structure, and that's for a couple reasons. A, fluorine is the most electronegative. So because fluorine is the most electronegative, it will never find itself usually in the center. And second, hydrogen here will never be in the center, because if you put hydrogen in the center, it will end up with too many bonds. So hydrogen always has to have on the outside. Hydrogen, as we also talked about, should never have dots around it like this or anything. Those are all wrong. Yeah. So hydrogen pretty much will just make 1 bond to the center atom. Now, the most important thing is really the next step, and that is the total number of valence electrons. So when you are counting up from a formula, you want to count the total number of valence electrons. Again, a reminder that the number of valence electrons equals the group number. So again, 1, 2, 3, 4, 5, 6, 7, and 8. So the number of valence electrons is equal to the group number. So that's a way you could do that. And when you're done, that number is really important, because that's exactly how many electrons your picture has to have. So once you figure out the total number of valence electrons, when you draw your Lewis structure, you should have exactly that number. You can't have any more. You can't have any less. It's got to hit that number like right on. Now, you may be asked to draw some Lewis structures for polyatomic ions. So if you remember, polyatomic ions are groups of nonmetals together that actually do have charges. So if something has a negative charge, that means that it has gained electrons. And that also means that you need to add to your total for that negative charge. And vice versa, if something has a positive charge, it means it has lost electrons. So you need to subtract from your total. And that's really important. Again, you need to adjust the total number of electrons for any type of charge that you see. If you don't do that, you'll probably end up with an odd number of electrons. And I'll say for our class, you should not end up with an odd number of electrons. It is possible, really, to have that. But for our class, everything will obey the octet rule. So everything, when it's all said and done, should have 8 electrons. Everything in terms of numbers, when you add up the total number of valence electrons, should also pretty much equal even numbers. You shouldn't end up with an odd number. So once you have the total number of electrons, the next thing that you want to do is draw one single covalent bond from the center atom to each of the outside atoms. And that's basically one line. So basically what you're going to do is you're going to go, I got my center atom, I got all of my outside atoms, however many you may have. I'm just going to draw one single bond to each of them. Again, you can use a line, you can use dots. I will use lines for the bonding electrons. And you can count up how many electrons you've used, 2, 4, 6, 8. For example, 8 used. And then the leftover electrons that you'll have will go on the outside ones in pairs until each of the outside ones have 8 electrons basically around them. And at that point, if you have used up all your electrons, you'll be done. If you still had more electrons, so let's just say you have something like this. And you're like, I still have more electrons. Then if you filled up all the outside ones with 8, then you go to the center and also put them on as dots or pairs of dots as well to the center atom. So once you've used up all your electrons, you filled up the outside atoms first until they have 8. Then you went to the center and filled it up. The next thing that you want to do is make sure that everybody meets the octet rule. And again, the octet rule means that they have 8 total electrons around them. The only exception is, again, hydrogen that should have just 2. And if something does not have 8, that is the point where you should make a double bond or a triple bond to try to fix it. So sometimes people want to always double bond or triple bond right out of the box when they're drawing these Lewis structures. Again, you only want to kind of use double bond or triple bonds to sort of fix something. So if something does not meet the octet rule, then you want to go back and try to fix it by making that double bond or a triple bond. And usually what you'll try to do in that case is use up all your double bonds first. And then if it still doesn't fix the problem, then you would move to your triple bond. All right, so let's take a look at one here and just sort of see how it goes. Okay, so we have NF3 here. So the first thing that you want to do is we want to count up the total number of valence electrons. So again, we're going to go to the periodic table. Nitrogen, which is group 5, has 5, plus our fluorine, that there are 3 of them, each in group 7, right? These represent our fluorine. And that is 21 plus 5 is 26 valence electrons. So when we draw this guy, this is our magic number here that we have to hit. We have to be exactly at 26 when it's all said and done. Now, logical arrangement between this guy and these guys is, since we only have 1 nitrogen and 3 fluorines, nitrogen is probably in the middle with everything attached to it. And in most cases, that is how most of these structures are. You typically have one center atom with everything else attached to it. There is possibility for more than one center atom, but that's a lot of times what you have. So for example, here, the logical arrangement would be to put our nitrogen in the middle. We could put our fluorines on the outside. And it doesn't matter, for example, for this top fluorine right here, that you could put on top or you could put it below the nitrogen. It doesn't really make a difference. Once we have our logical arrangement, this is our skeletal structure. The next thing that we want to do is just make one single bond between the center atom and each of the outside atoms. And at this point, we have now used 2, 4, and 6 electrons. So if we subtract that 6 off from our total, that leaves us 20 electrons still to go. Now, those electrons will go on the outside atoms first, again in pairs. So 2, 4, 6, 8. This one is full. 10, 12, 14. This one is full. 16, 18, and 20. So I'm sorry, I think I miscounted. 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. I'll learn to count one of these days. Try that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons. So we've now used 24 electrons, which leaves us just 2 electrons still to go. Everybody on the outside is full. So those last 2 electrons will end up right there, also as dots or pairs on the center atom. We have now used all 26 of our electrons. The last thing that we want to do is make sure that everything has met the octet rule. So if we look at this fluorine over here on the right, it has 2, 4, 6, 8. All the fluorines are exactly the same. 2, 4, 6, 8. 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. So this would be the correct Lewis structure here. Everybody has met the octet rule. We distributed all the electrons in their proper locations. Any questions on that? Okay. So why don't you try the next one here, and I'll just scroll through this so you can see it. All right, so why don't you take a second here. Now this one has a different sort of arrangement, so I'll give you sort of the structure for it, the way it's set up, and then you finish it up and we'll talk about it in just a minute. Okay, so let's take a look and see how we're doing. So this is nitric acid. So again, if it's something like this where it has sort of a weird or maybe a different sort of arrangement that you might not be familiar with, I would, much like here in this example, give you the arrangement. If I don't give you the arrangement, then usually what that means is kind of like the first one, there's a center atom, everything's connected to it. So we do want to figure out our valence electrons. So this is HNO3. So hydrogen is 1. Again, nitrogen is group 5. And there's 3 oxygens, each are 6. It's a lot of math right now, but I can go with 24, hopefully, if I did that right. So 18, 19, 24. Again, that's an important sort of number. So if we arrange it like I have it there, again, as you can see, I put the O up on top. You could leave it on the bottom like it was there. Either way is perfectly fine in terms of this O right here. Just draw a spot right there. Now, we want to follow the same procedures here. We want to make one single bond from the center atoms to each of the outside atoms. So we will end up with something that looks like this. Now, if we count it up, this is 2, 4, 6, 8 electrons. That leaves us basically 16 more to go. Those are still going to do the same thing. We're going to work outside in. So outside in when we adding those electrons. So when we go to hydrogen, you should hopefully know, again, hydrogen should not have any dots around it. It just need oh, I'm sorry. So how I figured out the 8 electrons were, when we count them for you, hang on here and change colors so you see it. So I think the question was, how did I get 8 electrons that I've used so far? So how I got 8 electrons I used so far is from each of the bonds that I made. So I'm just gonna go back over in blue. So right here is very badly drawn 2 electrons. This would be 4 electrons. This would be 6 electrons, and this would be 8 electrons. So those single bonds that you made between each of the atoms and the outside atoms, again, each line represents 2 electrons. So a reminder that if you use lines for bonding electrons, represents basically a pair of electrons or 2 electrons, right? One pair. So now that we've used 8 electrons, we still have 16 that we have to put on the molecule. Again, working on the outside in. We wouldn't put any more here on the hydrogen because it should only have 2, and that's the 2 that's right here. So we would go to our next outside one, which is say be this guy. So we'll go 2, 4, 6, 8, 10, 12, and that fills up this guy here. Also fills up this guy here. So we have now used, again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons now, total electrons. So we use now 20 total electrons, still now leaves us 4 electrons still to put on here. So again, the hydrogen is full. All the outside oxygens are full. So the next outside atom is actually right here. It's actually that oxygen next to the hydrogen. So we're going to go 2 and 4. And that now will be all 24 electrons are posted up here on our Lewis structure. Now, once we're done, we do need to make sure that we've distributed all the electrons, which we have. We then want to make sure that everybody meets the octet rule except for hydrogen to see if they're okay. So if we look at the hydrogen, it has 2 electrons, so it's all good right there. We look at this oxygen next to it, it has 2, 4, 6, 8. So again, 2 shared with the hydrogen, 4, 6, and 8 over here. We have this oxygen up on top, which again is sharing a pair with the nitrogen, 2, 4, 6, and 8. And this oxygen on the left-hand side here has 2, 4, 6, and 8. But now when we look at the nitrogen in the middle, the nitrogen in the middle, if we look at it, has 2, 4, 6. So the nitrogen here only has 6, does not meet the octet rule. Any questions on that so far? So at this point, we do need to fix that because, again, when you're done, everybody needs to hit the octet rule, or again, except hydrogen needs that too. So you may be tempted to go, can we fix it by doing this, perhaps? Can I just put a pair of electrons on the nitrogen? What do you think? You think that's right? If I do that and I put another pair on the nitrogen, if we think about our total number of electrons at this point, we'll now have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and you're correct. We now have 26 electrons, yeah? Which is too much, yeah? So we can't just put a pair of electrons on there because we will have more than the 24 electrons that we should have. Let's see, I should be able to erase that, I think. We'll get rid of that. So this is the part where we do want to fix it by making a double bond, or perhaps a triple bond if necessary. So we do have sort of 3 options as to where we can make our double bond. We can double bond to this oxygen. We can double bond to this oxygen. We could even double bond to this oxygen. To be truthfully honest with you, this oxygen right here, probably not your best choice in this situation. This bond between the oxygen and the hydrogen is essentially what makes it an acid. So we usually don't double bond into something like that. So we could choose either one of these oxygens over here on the left-hand side, so the guy on the top or the guy to the left, and we can make a double bond. So I'm going to go to the guy in the center, and if I just make a double bond by just drawing the line in, that also is not so great because if we look at it, I now have a couple of problems. I have over here on the top oxygen 2, 4, 6, 8, 10 electrons, too many. Although nitrogen does have 8, I now have too many electrons, and I also now have gone back to 26 electrons. So when we go to make a double bond or even a triple bond, what we actually need to do is take a pair of electrons. So for example, I'm going to take this pair of electrons and we're going to move it in to make that double bond. And when we do that, that means we should erase the electrons that we're moving in to make that double bond. And if we do that, we will end up with a picture that looks something like this. Now we move that line in to make the double bond. That will leave us with just the 2 electrons that are up on our top. We will have our 2 electrons over here still because we didn't touch them. We'll have our electrons over here because also we didn't touch them. And we will end up with this structure right here, where if we look at it, what we will see is we have for the hydrogen 2 electrons, oxygen 2, 4, 6, 8 electrons, nitrogen 2, 4, 6, 8 electrons, oxygen 2, 4, 6, 8, this oxygen 2, 4, 6, 8. Everybody has 8 valence electrons. And in addition to 8 valence electrons, the total number of valence electrons that we are using is still 24. So we still have the correct number of electrons. Now you could have, if you wanted to, done the double bond to the guy on the left. And if you drew the guy on the left as the double bond, it would have looked something like this. And either one of these molecules would have been perfectly fine to draw for the Lewis structure. Yeah, so the question is in terms of the dots for the double bond, I ended up putting them on the side here, and that's typically how you'll see the lone pairs with the double bonds. You'll typically see them on the sides. Truthfully, it doesn't matter. You could, for example, let's draw it into here. So you could have, if you wanted to, done something like this. I think you're asking, you could have left it technically like that. It's not technically wrong or anything like that. Typically, people will move the double bond, those electrons to the kind of the sides like it is in my picture, but you don't have to. The key rule on it, just like a normal Lewis dot symbol, is no more than 2 electrons per side. So you can basically just put them however you want. Now, if you did draw this other structure over here, they are related to each other, and sometimes people use this type of arrow to relate them to each other. And these are what are known as resonance structures of each other. So a resonance structure is basically 2 or more Lewis structures that can be drawn for the same molecule. And it's because one Lewis structure doesn't adequately sort of explain what's going on, because really these double bond electrons that we have, to draw it like this maybe. So although the double bond is, say, on this guy, it could be at some point over here to the guy on the left. They're sort of what are known as delocalized, or sort of moving around from one side to the next. So at any given moment, it could look like that. At some moment, it may look like this structure. The true structure is probably somewhere between them. So sometimes you can draw what's known as a resonance structure. It usually happens when you have sort of more than one option as to where you could put that double bond. And you can draw an equivalent structure that has basically the double bond in another location, sometimes a triple bond, but a lot of times it's a double bond in a different location. Any questions on how to draw that? Again, for our purposes, if you weren't asked to draw the resonance structure, you could either draw this structure over here on the left, you could draw the one on the right. It's probably perfectly fine. Any questions on that one there? Scroll through that there. All right, so why don't you draw the one for carbonate here, see what you come up with, and we'll talk about it in just a second. Okay, let's take a look here. So again, want to figure out the total number of valence electrons. So we got carbon, which is group 4 on the periodic table, plus 3 times 6 for our oxygens. And now we do have a -2. So remember, minus means that it gained. So in this case, you do need to add those two in to your total. Otherwise, again, you're going to be short in terms of how many electrons you should have. And that looks like a 24 valence electrons. Again, 24 is our number here that we do have to hit. In this case, we have 1 carbon and 3 oxygens. So logical arrangement is carbon in the middle. Everybody else is on the outside, going to be bound to it. We're going to make, again, 1 single bond from the center to each of the outside atoms. So at this point, we've now used 6 electrons. That leaves us 18 more to go. And those, again, will go on the outside until everybody has 8 on the outside. So that's 2, 4, 6, 8, 10, 12, 14, 16, and 18 at that point. At this point, if we count up the total number of electrons that we've used, everybody we have a total of 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons coming around. So we do want to make sure everybody's good. So our oxygen on the outside, again, has 2, 4, 6, and 8 electrons. Each of the oxygens are identical on the outside, so they all have 8, so they're good. But when we look at our carbon, it's got 2, 4, 6 electrons. It is not good. Again, only has 6 electrons around it. So again, here we want to make a double bond to try to fix it. And we can make a double bond, in this case, to any of the oxygens that we like. They're all perfectly identical to each other. Again, different than the previous one. We don't have a hydrogen hanging off of here. So we actually could double bond anywhere you would like. So again, I'm going to make a double bond by not just adding electrons, but I'm going to make a double bond by taking a pair of electrons. So again, I'm going to do it from the top one first here. I'm going to take this pair of electrons, and again, I'm going to move them in to make my double bond. And when I do that, I'll try not to advance that yet, but when I do that, I will end up with something that looks like this, the double bond there. This guy still has all of his electrons. Very badly drawn there. Let me fix that real quick. I almost got it there. Try that. So this guy also, again, still has its electrons around it as well. At this point, we have 2, 4, 6, 8 electrons around the oxygen on top, 2, 4, 6, 8 electrons around the guy on the right, and also 2, 4, 6, 8 electrons to the oxygen on the left. Our carbon now has 2, 4, 6, 8 electrons. We still have only used 24 electrons. And typically speaking, if it is something with a charge, like a polyatomic ion, once you draw the Lewis structure, typically put little brackets around it, and the charge on the outside is typically the way you do that. Any questions on that structure there? Now, for this particular one, you could draw another structure, which would be a resonance structure where perhaps we made the double bond to the oxygen on the right. And it would look something like this. And you could actually draw a third structure for this, where we made the double bond on the left, which would look like this. We got a box in the way. I'm going to move out of my way. There we go. That's a big O, but we'll work with it. And it would look like this as well. So for something like carbonate, you actually could draw 3 resonance structures. And again, it's because those double bonded electrons are pretty much moving from one location to the next. They could be at any oxygen at any given time. And so that's why you could draw any of these 3 structures. Again, if you're not asked to draw the resonance structure, which you probably won't be in this class, if you drew this one for carbonate, it's good. If you drew the middle one by itself, it's good. Or if you drew the one on the right, it is also okay as well. So again, if you're not asked to draw the resonance structure, you could draw any one of the 3 sort of structures that you see on the screen. If you are asked to draw the resonance structures, all the resonance structures, then you should draw them all, obviously. But if you're not asked to do so, you can do any one of the 3. Any questions on that there? So again, if you follow these sort of steps for drawing these Lewis structures, like we talked about and like we've been doing on these, they should lead you to a correct, pretty good structure when it's all said and done. So let me give you a few more just to practice here, I think. Why don't you draw the Lewis structures? Why don't we go with, why don't you draw CO2, NH3, SO2, N2, and then why don't we do C2, H5, Br. So why don't you take a few minutes here and try to draw the Lewis structures for these, just to make sure everybody's on the same page, and then we'll go through each of those. Okay, so I know you may not be finished with all of them, but let's start going through some of them and see how you're doing. So let's start with the CO2. All right, so again, we want to figure out our valence electrons here for our CO2. Carbon being group 4 is 4. There's 2 oxygens, each at 6, so that's 12. That is 16, if my math is right there. So again, here we have 1 carbon and 2 oxygens, carbon being further to the left on the periodic table than oxygen. If you look at it, they're in the same row, our period, which means it's the least electronegative. So carbon should be in the middle, or oxygen should be on the outside. We're going to follow the same process. We're going to make 1 bond from the center to the outside. That now is 2 and 4 electrons. That gives us 12 more to go. Again, on the outside first. So 2, 4, 6. That fills up that guy. 8, 10, 12. That fills up that guy. I have now placed 2, 4, 6, 8, 10, 12, 14, 16 electrons on my picture. That is the total number of electrons that I should have. We do want to make sure everybody has 8. So if we look on the oxygen on the right, it has 2, 4, 6, 8. The one on the left has 2, 4, 6, 8. Carbon, though, in the middle has only 2 and 4. So carbon, not so good. So we need to fix it. So we're going to make a double bond to try to fix it. At this point, we could make the double bond in either oxygen. Again, a reminder that when we make the double bond, we're going to take a pair of electrons and move them in. So if I do that, that will give me a double bond on the right-hand side. And now I have 2, 4, 6, 8 for the oxygen, 2, 4, 6, 8 for the oxygen on the left, and 2, 4, 6 for our carbon. It got better. It went from 4 to 6, but still short. So in this case, we actually need to make a double bond on the other oxygen because we have that ability. So again, you don't want to just jump to perhaps a triple bond in this case. Since we do have the ability to make another double bond, we want to make that double bond first. And if we bring those electrons in on the left-hand side, I'll answer your question in 1 second about the electrons. So when we take the electrons in from the other side and make our double bond, we will end up with something like this. Now, your question, I think, could be answered with this picture as well. So let me just go on this picture here and show you. So when we do bring I'll get to your question about the position in 1 second, just to make sure I'm answering it correctly. So let's start with the electrons. So when we move our electrons in, we now have, for example, 2, 4, 6, 8 electrons. So counting the guy on the right, he has 2, 4, 6 electrons and 8 electrons there on the right. Same thing if we went to our guy on the left, he would now have 2, 4, 6, 8 electrons. Remember that those electrons are being shared between, in this case, the carbon and the oxygen. So even though we bring those electrons in, they actually are still maintaining the 8 electrons because they are being shared. And then for our carbon, it has, let's go over these, 2, 4, and 6 and 8 electrons as well. So everybody does have 8 electrons, even when we bring those electrons in from the outside to the inside. They're still attached to the oxygen. They're just being shared now between the oxygen and the carbon, as to before they were not being shared. That good on the question on the electrons there? And then to answer the question, I think about position of the element, and you could correct me if I'm wrong, but I think you're asking, is it okay if you maybe draw it like this, like in this orientation? And if that's your question, it's perfectly fine. It's just most people sort of draw these guys kind of just straight like this, but truthfully, it's the same thing. It's just turned in a different direction. It's okay. And that's also why, say earlier when we had this guy, we put I won't draw all the electrons in, but we put this fluorine on the bottom. And I think when I drew it, I moved that fluorine up on top. It's okay in that situation. Again, if you put, for example, the fluorine on the top or the bottom, it doesn't really matter. That good? Any other questions? Did I get them all? Yeah. Okay. So in this case, in order for everybody to get to that octet rule, we had to make 2 double bonds in this case, and that allowed us for everybody to get there. Again, if you do a total count all the way around, we still have only 16 electrons in this case, but everybody was able to get to that 8 electrons. Other questions on that? All right, so let's take a look then at our NH3. So our nitrogen is group 5. Our hydrogen, there's 3 of them. Each of them is 1. That is 8 electrons when we draw this picture. In this case, nitrogen is going to go in the center. Remember that hydrogen cannot go in the center, so it has to go on the outside. We're going to follow the same process here. So we're going to make 1 single bond to each of the outside ones. That is now 2, 4, and 6 electrons. That means we have 2 more to go from our total. We won't put any on the outside because they're all hydrogens. So as soon as hydrogen makes that bond, it's done. It has 2 on all of them. So since all the outside ones would be full, those last 2 electrons would end up over here on the nitrogen. And in that case, what that means is hydrogen has 2 electrons, each of them. Nitrogen now has, again, 2, 4, 6, and our 8 electrons up on top. Everybody's perfectly good and happy. That would be the correct structure. Any questions on that one? Okay, looking at SO2. So SO2, sulfur is 6. There's 2 oxygens at 6, so that is 18 valence electrons here. So we have 1 sulfur and 2 oxygens. Again, if you look at the periodic table, looks like this. Sulfur is lower on the periodic table, so it's less electronegative. Also, since there's only 1 of them, it's going to be in the middle. Oxygens will be on our outside. Again, we're going to follow the same procedure. We're going to do a single bond from our center to our outside atoms. That's going to be 2 and 4 electrons. That's going to leave us 14 more to go in this case. So filling up the outside, 2, 4, 6, 8, 10, 12. At this point, outside ones are full. I have now put on there 16 electrons. I actually still have, as you can see, 2 more to go. Those 2, just like before, will come to our center atom as a pair of electrons. At this point, we have now put all 18 electrons up there. We want to make sure everybody is good. And if we look at our oxygens on the outside, our oxygens on the outside has 2, 4, 6, and 8 electrons. So 2, 4, 6, 8 electrons. Oxygen on the right, exact same thing, 2, 4, 6, 8 electrons. But again, our sulfur here in the middle has 2, 4, and 6 electrons. So sulfur not so good. So here we want to try to fix it by making a double bond. We have two options. We could double bond on the left. We could double bond on the right. I'm going to take a pair of electrons from my outside one. Again, I'm going to move them in. And when I do so, I will end up with something that looks like this. Our double bond has now become there. And we look something like this. We now have 2, 4, 6, 8 electrons on the right, 2, 4, 6, 8 electrons on the left. And our sulfur has 2, 4, 6, 8 electrons here. Also could draw a resonance structure for this guy where the double bond would just be to the right instead. Again, you don't have to draw both of them, but you could draw either one of these structures and they would be perfectly fine. Everybody has a really important to follow the rules that we're doing here. Again, that is how we get these non-bonding electrons on the center atom because they should have. Yeah, so your question about would it be wrong if you did, I'll just draw it over here real quick one more time. So at this point, so I think your question is, could you just add electrons here? And you couldn't add electrons here because you would have too many. Even if you took those electrons away and did it this way, it would still be wrong because really those electrons aren't moving to this per se element. What this would mean is if you just did the dots, these are non-bonding electrons, which means these electrons are no longer being shared with the oxygen, which would leave the oxygen 2, 4, and 6 electrons only, which would then make the oxygen short. So you do have to turn it into a double bond like we did down here. That way, these electrons that make the double bond count for both the oxygen and the sulfur, and that allows both the oxygen and the sulfur to maintain 8 valence electrons and be happy. Again, even if you scratch out the electrons here and put the dots on the sulfur, it would in that case just move your problem from the sulfur, to the oxygen because the oxygen wouldn't have enough. Other questions on that? Okay. So again, if you're not asked to draw the resonance structure, either one of these perfectly good, not a problem. They're both basically the same structure. All right, then let's take a look at N2. So N2 is nitrogen, diatomic molecule the way it comes. So since there's 2 nitrogens, 2 times 5, which is 10 valence electrons. In this case, there really is no center atom because it's diatomic, so there's just 2. But you really can follow the same procedure as what we did before. You want to follow and make just a single bond between them. That's 2 electrons. That leaves us 8 to go. And you can just follow the same procedure. So fill out the outside one first. So 2, 4, 6. He's done. And we would have 2 more to go here, which would be him that. And that's 2, 4, 6, 8, 10 electrons. When we look at the nitrogen on the right, it has 2, 4, 6, 8 electrons, so it's fine. When we look at the nitrogen on the left, it has 2 and 4. So our nitrogen on the left there has only 4 electrons, not so good. So here we want to try to fix it by making a double bond. So same process, we're going to take a pair of electrons and move them in. And when we do that, we will end up with something that looks like this. Again, still has 10 electrons. Nitrogen on the right has 2, 4, 6, 8. Nitrogen on the left, 2, 4, 6. So by making that double bond, it got us closer, got us to 6 electrons for the guy on the left. But that is still not good because he doesn't have 8. So we're going to actually now has to move to a triple bond. So same process, we're going to take another pair of electrons and move them in. And when we take that pair of electrons and move it in, we will end up with a triple bond between them. and we'll end up with our non-bonding electrons that were there before. And this is how we get to nitrogen that ends up with a triple bond. Nitrogen on the right has 2, 4, 6, 8 electrons. Nitrogen on the left has also 2, 4, 6, and 8 electrons. Any questions on that? So that's a nice example of showing you how we get to a triple bond. But usually that's how you want to go to a triple bond, is if you perhaps make a double bond and you used up sort of all your options there and it still didn't fix it at that point, then you want to move to a triple bond. Any questions on that one? So looking at our last one, and I'll just put this one up here. This is sort of what is referred to as an organic compound. I don't recall. Sometimes in labs and stuff, they go through some of these organic guys. So basically, an organic compound is basically made up of like carbons, hydrogens, oxygens, and some other things. But the basis of how organic guys are bound together is carbons are bound to carbons, and then to those carbons, we have hydrogens attached. So we could take sort of the same approach here. We have 2 carbons. So if we do our C2H5Br, so we have 2 carbons, each at 4. We have 5 hydrogens, each at 1. And we have bromine, which is 7. So that's a lot of math. Then you go with 8, 15, maybe 20, if I'm not mistaken in that case. That's good. Maybe use the calculator if you need, but let's see. So the logical arrangement in this case is we're actually going to have carbon attached to carbon. So we'll have a couple of center bonds, center atoms. And again, usually the carbons and the hydrogens are bound together. So you could put, for example, 3 hydrogens over here. You could also put a couple of hydrogens over here. And you could put like a bromine over here. So typically when you have carbon, it wants to make 4 bonds. So typically when you have carbon involved, it really does what you usually want to make 4 bonds. So that's why I could figure out I could put 3 more here because it's going to bond to the carbon. I could put 3 more on this side because it's going to also bond to the carbon, which would give it 4 bonds. We would follow our same procedure. So if you did 1, 2, 3, 4, 5, 6, and don't forget to connect here, we'll give you 7. And if we count up how many electrons we use there, 2, 4, 6, 8, 10, 12, 14 electrons. Leaves us 6 electrons to go. Again, we're going to go on the outside first. So when we go on the outside, we have hydrogen, 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 and hydrogen. All those hydrogens are good, right? Because they already have 2 electrons. So the next outside one, we could put those on or right here at the bromine. So we got 2, 4, and 6. And that means that this hydrogen is good too. All the hydrogens are good. They all have 2. Bromine has 2, 4, 6, 8. This carbon on the left has 2, 4, 6, and 8. Carbon on the right has 2, 4, 6, and 8 as well. Everybody has met the octet rule. Everybody's perfectly fine with each other. You could do that as well. So that sometimes when you find something that has a lot of carbons in it and hydrogens, it's some type of organic compound, and usually they're connected like this: carbons to carbons, hydrogens attached. Sometimes other things like we see over here, the bromine, for example, is attached as well. So, you know, that's typically how organic guys look. In terms of this bromine, although I did put it on the bottom right there, technically speaking, because there's only one bromine, really, you could have drew the bromine here. You could have drew the bromine here and just put the hydrogens on the bottom is perfectly fine. And actually, you could have drew a bromine here, any one of these places, and then obviously move the hydrogens around, kind of like what I just did over here. These two structures here, these are actually not resonance structures. They're actually the same structure. It's just turned. So they're actually the exact same structure. So that's a way that if you come across something that's sort of organic that has carbons and hydrogens involved, that's typically the connection, carbons to carbons, and then hydrogens attached to those carbons, and occasionally the hydrogens get swapped out for something else. For lecture, probably won't come across too many in terms of organic type compounds, but I put it up there because sometimes in labs and stuff like that, they like to put a lot of organic ones for you to draw and stuff like that. So the stuff that we'll draw probably be more above the green line here, and the stuff that we did above it and on the previous examples, probably not too much, if any, organic type compounds. I don't think you'll have to draw. Any questions on how to draw Lewis structures? I took the day here to draw Lewis structures, but hopefully this makes sense. Any questions on any of it? Okay, so we're almost done with this chapter. We're just going to talk about actually some geometry and stuff like that. And then we'll be done with it. We'll be on to the next one. But to answer your question, that is absolutely correct. So hydrogen in a Lewis structure, no matter where you put it, A, should always be on the outside. It should pretty much always look like this. It should never, ever have any dots. Yeah. Because hydrogen then would have 8 electrons, and that's too many. In addition, hydrogen should never be double bonded, too many. Hydrogen can never be triple bonded either, too many electrons. So pretty much in a Lewis structure, hydrogen should always look like this on the outside. And that again is because the whole goal of bonding, like we talked about, is for everybody to get to those noble gas configuration. And if you look at hydrogen on the periodic table, it's number 1. And the only guy it needs to get to is helium, which is a noble gas. And that's why, again, hydrogen only needs basically 1 more electron or 2 total electrons to become like a noble gas. So hydrogen should always look like what's in the box there on the right. Pretty much one line with the hydrogen, never dots, never double bonded or triple bonded as well. Other questions? Okay, then we will pick up on Wednesday, and we'll finish this chapter. We'll hopefully roll into the next one, which I think is balancing equations and chemical reactions. So hopefully before Wednesday, up online, there'll probably be a new set of lecture notes for the next chapter, which we're going in order here, which I think should be chapter 5, if I'm not mistaken. So that will be coming up. I'm thinking also maybe sometime next week, maybe Wednesday or something like that, we may take a quiz on sort of this stuff here, the naming and the Lewis structures and stuff like that. So just to give you a heads up, probably sometime next week towards the end, we'll probably take some type of quiz sort of on this stuff. So keep that in mind as you're kind of studying and thinking about this week. Any other questions on anything? And I'll let you know on Wednesday for sure. Again, the quiz would not be this Wednesday, next week. All right, have a good one. I'm going to end the lecture today. If you have lab, have a nice one. Make sure you go to lab, a visitor, say hello. Thank you. You guys all have a good day as well. I'll see you on Wednesday.